Hey, good evening, guys.
Good evening, teacher.
How are you guys?
Fine, thanks, and you?
Okay, guys. Now, how are you today?
Fine, thanks.
Yeah, well, I'm fine too. Also, now we are going to start our lesson. Our today's topic is about the very important thing in our life, that is optimization. To optimize the values, quantities, some quantities that are very important in our life. Okay, guys. Now, in this semester, in this term, we have learned about derivatives. You know that? Yes. We have learned about application of derivatives, and one of the next topic is about optimization. Before that, we are going to review that. Okay, if you remember, what was the derivative was? Derivative is, we will use the derivative to find what? Maximum or minimum values. Yeah? Yes. Okay, maximum value. Okay, let me show you something interesting. Yeah, I'm going to juggle you now. Now, I'm going to juggle with 3 balls. Okay, now here the thing that I want to explain is that the derivative is about what? About maximum or minimum value of some quantity. Yeah. If you remember, we said that the physical meaning of the derivative is instantaneous velocity. Velocity at that time. Yeah, we will use that derivative to find the highest point of the ball. When I throw the ball, G gravitation pulls down the ball, and the ball catches the highest point when the velocity is what at the top velocity is the vertical velocity is equal to 0. Yeah. Okay. Now let's juggle. Okay. I just see here these 2 balls. When I throw them up, you know that the G gravitation is pulling that 2 balls here. And at some point, its velocity will equalize to 0. At which point? At the highest point, maximum point. Yeah. Okay, guys. Now we find the vertical position. Vertical position time graph on the vertical position time graph. If we derivate that function, we will get the function of the velocity, and if you equalize that velocity to 0, we will get the time when the velocity, when the ball will be the highest point. Okay, that's correct. As you see, I can juggle with 3 balls. Also, I can juggle with 4 balls. Now, not now, but in the next lesson. Okay, guys. Now, let me show you a video. And get to the video. Okay, here you see a video. Okay, here you see. Okay, guys. Now the guy in here, one of your friends, is throwing the ball, and that ball will hit the basket. Yeah. Yes. Will hit the basket, and the ball also reaches the maximum point when time flight, when velocity or vertical velocity is equal to 0. Yeah. If you remember, we have also said that the geometrical meaning of the derivative is the slope of the tangent line at that point. Slope of the tangent line at that point. Okay, now the slope derivative. This is a derivative of the function at this point. Derivative of this function at here at the top is equal to 0. 0, yeah. And then if the derivative is 0, then that one is the highest one. Okay, now that's correct. Okay, guys. Now let's remember that some topics from the physics. Yeah. Or before that, some topics from our previous years. In algebra, we have learned about the what? Quadratic functions. Do you remember that?
Yes.
What was that quadratic function there? This one. F of x is equal to ax squared plus bx plus c is a quadratic function. What is the graph of the quadratic function? Yes. The quadratic function is parabola. Okay, now here I'm asking you a question.
If we will show it on the parabola, if we will show it on the graph, it will seems like that. If we want to find the vertex, of this parabola, we should take the derivative of this function.
2ax, yeah?
Yes.
Okay, 2a times x. That's correct.
And equalize it to 0.
Yes. One mistake there is plus b must be. Okay.
Yes. And if we want to find the vertex of this function, we find it by this formula, minus b over 2a.
Okay, now this is the x coordinate of vertex of the parabola. Is this correct?
Yes.
Okay, you know that from the previous year, but you don't know the proof of this one, yeah? Okay, with the help of derivative, we can prove that the vertex of the parabola, we will find that with the help of this formula, yeah? Okay, now let's remember the physics, yeah? Do you like the physics?
Yes.
Have you learned about the projectile motion?
Yes.
About the, now, velocity and time and distances, yeah?
Yes.
Okay, guys, now then, let me write here some formulas from the physics. You know that. How do we find the final velocity? What is the final velocity equal to? Velocity final is equal to? Velocity initial
Multiplied by time.
No, not plus 80, yeah?
80, yes.
Okay, this is about the motion with in one direction, yeah?
Yes.
Okay, what about the motion in two directions? For example, we have a vertical and horizontal position, yeah? Projectile motion here, if you remember.
Yes.
If I throw the ball here, for example, to Bachat, you can catch that, yeah?
Yes.
Why? How your brain works. Okay, can you throw me that? Okay, now, for example, if I throw that Abizar catch that ball, yeah? Okay, why? Because his brain, he sees the ball. At what angle and at what velocity I've thrown the ball. And his brain takes that information, analyzes that, and he and then he can easily catch that ball, yeah? His brain senses it to his now arm, and his arm can easily catch that ball, okay? Okay, now we are going to speak about that projectile motion that you have learned in physics. Okay, this is a ball that I am throwing to what? Who? Abizar. Okay, now this ball has now V initial here. This is a V initial. Here at some angle I am throwing that ball, yeah?
Yes.
Okay, now the question is what must be the maximum height? Yeah? I want to find the maximum. We said that derivative about the maximum height and the maximum and minimum values, yeah, of something. Yeah, we are going to find. Find the maximum height and what distance. Okay, here you have learned this formula also. Vx is equal to
V initial multiplied
time
minus
now here x is equal to v initial times time minus 1 over 2 times gt squared. This is about the motion in one direction, yeah?
Yes.
But we are speaking the motion in two directions. That means when we find the height, we will use the velocity. Which velocity? Now, vertical velocity, v, y, yeah? How do we find the velocity, vertical velocity? V initial times, okay, sine alpha, let's go to sine alpha. And times time minus 1 over 2, g plus. And this is a height
depends on time.
which depends on time, yeah?
Yes.
Okay, well now this is a function height that depends on time. I want to find the maximum height. How can we find the maximum height? Okay, solve this please.
Height is derivative.
Okay, when you have to take the derivative of the function.
V initial multiplying sine alpha minus 1 over 2 multiplied 2 gt is equalized to 0. And 2 is cancelled. And so V initial multiply sine alpha equal to gt. So t rise equal to V initial multiply sine alpha over gravitation.
Okay, now is this correct?
Yes.
Okay, guys, here we found that at what time this height will be maximum.
Yes.
Yeah, this height will be maximum. Height will be maximum when the time is equal to V initial times sine alpha over g. And this time we call the time rise, yeah? Do you remember that?
Yes.
Time rise, you know that from physics. Also we have what time fly, yeah? What can you say about time fly? Time fly is the twice of
Time rise.
time rise, yeah. Time fly is twice of
Time rise.
2 times the time fly, that is sine alpha over.
Over g.
Now this one was about the vertical maximum height.
Yes.
Now about horizontal distance, maximum horizontal distance. Okay guys, now what must be the horizontal, now I'm going to throw the ball up at some, now, constant velocity at some angle, yeah? For example, if I throw the ball here like this one, or this one, yeah? There is a difference between angle, yeah?
Yes.
Now, if I throw the ball up, and what must be the, now at constant velocity, what must be the angle that reaches the highest point, yeah?
At what angle? Yes.
At what angle, okay. Okay, now let me show you here. To find out where going to, you have to use what? This formula, yeah? But without this part, because what?
It's vertical. Yes, it depends on time.
It's the vertical, yeah, here, but we are going to find horizontal.
Yes, it depends on time.
Yes. G, because G is pulling downwards. Yeah. Okay, that's all. We will not do G because it's now in horizontal, in vertical position, direction. X is equal to V initial times that. Now we will use which velocity? Yes.
Cosine.
Cosine, vertical, horizontal velocity. Yeah?
Yes.
Here we use the vertical velocity, but here we will use the horizontal. To find horizontal velocity, we will multiply V initial with cosine alpha time fly, yeah?
Yes.
Time fly. Okay guys, now here x is equal to V initial times cosine alpha times time phi is equal to twice of
Can I solve it?
okay, come here, sine alpha. Okay guys, now this is a function that depends on what? Alpha.
Yes.
Okay, you have to find at what value of angle this will be.
Yes, it will reach a maximum.
This height, maximum distance. Okay.
So it will be V initial multiplying by cosinus alpha or cosinus alpha multiplying V initial multiplying sinus alpha over G. So it will be like that. V initial square multiplying by sinus 2 alpha over G.
Yes. Yeah. Is this clear? You know that, yeah?
Yes.
That
Yes.
2 times sine alpha times cosine alpha will give us sine 2 alpha. Yes.
Yes.
Okay.
So
We have to.
like that. 2 over cosinus.
Yeah. Now here we are going. Okay. What do you mean, please?
It means that sinus 2 alpha is equal to 2 multiplying by cosinus 2 alpha.
Yeah. We are going to. We have
Derivative
yes.
or
Derivative.
derivative, yes, and we must equalize it to 0, so it will be cosinus 2 alpha equalizing to 0, and 2 alpha is equal to P over 2. P is equal to 180. So
we can change the p with 180. Yeah.
And alpha is equal to p over 4, and it equals to 45 degrees.
Yes.
So we must so from 45 degrees, so it will be reach maximum height.
Okay, thank you so much, Sanjay. Okay, is this clear?
Yes.
Now that means I have to throw the ball with 45 degrees with a constant velocity that will reach the maximum horizontal distance. Yeah.
Yes.
Okay, that's correct. Okay, guys. Now let's continue. Now this one was about what? All about was the parabola, yeah? But we are going to look at here a cubic function, yeah? Now if you remember, we have learned about what here, what we call this point?
Maximum.
What?
Minimum.
Yeah, local maximum, local minimum points we have learned. Also we have learned about the inflection point, that is approximately here, yeah? The point in where the graph changes from concavity down to concavity up, yeah? Okay, guys. If you, I said, no, we know that here the derivative is the, what? The geometrical meaning of the derivative is just the slope of the function at that point, yeah? Slope of the tangent line at that point. Slope of this point, slope of this tangent line is m here. You can see that? Can you see that?
Yes.
Yeah, m here, and that is, okay guys, wait a minute. No, slope of this tangent line is 9.27. As I move the point, slope is decreasing, yeah?
Yes.
7, 6, decreasing.
5, 4, 3.
And at the top, slope is equal to 0. That means derivative is equal to 0.
Yes.
Derivative is equal to 0, and it's continued to decreasing. And somewhere here, the slope is minimum, yeah?
Yes.
Slope is minimum. That means we found with here what? Inflection point. After that, if I continue that, somewhere here also the slope is equal to 0. That means we will find the local minimum here. Yeah? Is this clear?
Yes.
If I continue. Okay. We had a cubic graph, cubic parabola, and I took the derivative of the function. It changed to the quadratic parabola. Yeah?
Yes.
Now, if you remember, now, if we take the derivative of the quadratic function, we will get a straight line. Straight line, yeah? Okay, now, straight line. Okay, then here, this is a cubic function, local maximum, local minimum here, in where the slope of that function is equal to 0, derivative of that function is equal to 0, as you see.
Yes.
And here we have an inflection point. At the inflection point, the slope, derivative of the first function is minimum. And derivative, that means the second derivative is equal to 0. Okay? Is this clear?
Yes.
It was not so easy, yeah?
Yes.
Or it was easy?
It's not.
No, it's actually it's not so easy, but you are the clever, yeah?
Yes.
I know you are the cleverest students that I have ever seen, man. Okay, guys, let's continue. Okay, now everything that we have learned are in here. We reviewed that, yeah? Now we are going to start a new topic that is called optimization. The application of derivative optimization. What is optimization? And where we use the optimization? Optimization is one of the important topics of the mathematics. In our daily life, we have to optimize some quantities. For example, we want to maximize some quantity. For example, gain in something where we gain. I want to maximize the gain. I want to minimize the loss. Yeah. And we want to minimize the waste of material of something here, for example. And then in there we use the derivative. Okay, this topic we will today we are going to start. Okay. Okay, guys, optimization problem. Here, now optimization problem. Okay, optimization problem. Now, to optimize means to maximize or minimize some quantities. Yeah, that means to take the derivative of the function and equalize that to 0. Okay.
Yes.
Okay, look at it here. Now, to make, in this topic, we have some rules. To optimize the quantities, we have to follow some rules. They are in here. They're in here. Okay, the first rule is determine the quantity to be maximized or minimized and label it with the letter M. Say for M for that. The quantity that I want to maximize or minimize. In this task, it was the height and displacement, yeah, horizontal distance. And this is the quantity I want to maximize. The first task. Assign the letters now and label it with the letter say M, for example. Label it, yeah. Denote that with some letter. For example, here it was H, and here it was X.
Yes.
And assign the letters for other quantities. Assign the letters for other quantities, possibly with the help of a figure. We have to assign letters for other quantities. Here there was time or alpha in here. And express M in terms of some other variables. Express M, write M in terms of other variables. Write H in terms of other variables. T in here, for example. Yeah? Only here one variable we have, T. And we can express the quantity in terms of some more than one variable. Okay, the fourth one, use the data in the problem to write M as a function of one variable. This is very important, yeah? Because if there is a two variable, we can't find the derivative of that function. Because this is the topic of university. You are learning that in university, yeah? To find the derivative of function with two variables. Now in here we have a function, as you see, that depends on only one variable, T, yeah? Okay, now find the domain of the function of possible values of M, which values cannot be M, possible values of X, and find the maximum or minimum value of M of X with the help of the first derivative. Oh, here's the first derivative. This is the topic that you know, yeah? You can find the derivative of the function. Yeah. Okay, let's solve example, yeah? Okay? Yes. Okay, guys, now let's here solve this one. Can you see this?
Yes. Yes.
Okay, guys, now the first one. The task is a man has 40 meters of fencing. 40 meters of fencing that he plans to use to enclose the rectangular garden plot. Find the dimensions of the plot that will maximize the area. What is the fencing here is this one. And he wants to enclose his garden with this one. In rectangular shape. Okay? And the length of that fencing is 40 meters. The whole length of that fencing is 40 meters, yeah? Yes. And he wants to what? He wants to maximize it. He's very clever, yeah? He wants a bigger area. He wants to maximize that area. That's why now we are going to help that man. We are going to help that man to say here the dimensions of this rectangular shaped garden, yeah? That will maximize his area. Okay, this is the question of optimization problem. The first, we said that we have some steps that we are going to follow. The first step is determine the quantity to be maximized. What we are going to maximize?
Area.
Area, yes, that's correct. Area. And label it with a letter, capital A, let's place it here. Yes. And assign letters for other quantities with the help of the figure. Assign letters for other quantities, yeah? Now here to find the area of rectangle, what is it? What do I have to do? Area of the rectangle.
Multiply two diagonals.
Yeah, two sides. Yeah.
Yes.
We will now denote this side with A and length with B. Yeah. Okay. Now that area is equal to the third step is express them in terms of some other values. Write the quantity in terms of other values. A is equal to A times B. Is this clear?
Yes.
Now, here we have A is a quantity that depends on two variables, A and B.
Yes.
Okay? But we want only one variable to take the derivative, yeah?
Yes.
Okay, now the next one is use the data in the problem. Use the data in the problem, the given information in this problem, to write M as a function. To write A in this case as a function of one variable. Here we have two variables. What the data in here is given. What the information in this here is
40 meters.
40 meters, that's correct. Now the length of this card is 40 meters, yeah?
Yes.
What is the length in here? It's
Length or
yeah, whole length is the perimeter of the rectangle, yeah?
Yes.
How do you find the perimeter?
A plus B.
A plus B times 2.
Yes.
It's equal to 40 meters.
Yes.
A plus B, just A plus B is equal to
20.
Yes, that's correct, 20. We will use this information. Now, just to write this one as a function which depends only on one variable. For example, at B, I want to write that A as a function which depends on B. That means I have to change the A, yeah? I have to write the A in terms of what? B. What is A in here then?
20 minus B.
Okay, that's correct. I said you are the cleverest man. Now times B.
Yes.
Okay, then this is equal to 20B minus B squared, yeah?
Yes.
Okay, now this is area which depends on B. I got the function, yeah? I want to maximize this one. What I have to do? You can solve that this one. What I have to do to maximize the area?
Equalize.
No, first
Yes.
derivate the function, yeah?
Yes.
20B minus B squared.
Yes.
Okay, who can derivate this one? Asghar, can you derivate? Okay, this one is very easy question for you. I know that. Okay, that's correct. Can I continue?
And we symbolize this to 0.
And then
Now E2 is cancelled. It's
is equal to what?
B is equal to 10.
Okay, guys. Now, thanks to our Asghar, that he solved that. Okay, as you see here, the what? B must be equal to 10. Okay, if B is 10, then A is what? It's also 10, yeah? That means B must be equal to A. Okay, B is equal to, both of them are equal to 10.
Yes.
Okay, if then our rectangle, if it's now, if it's what? If it's rectangle, if it's square, then it will have the maximum area. Okay, we will say that to man. You have to if you want to maximize your garden, you have to make that in square shape. Okay?
Yes.
Okay, guys. Now let's continue. Next topic is let's. Yeah, let's solve the next question. Yeah, this one. A little bit harder than the previous one. A manufacturer has an order to make cylindrical cans. manufacturer, they want to make a can, this was our example, with a volume of 5 centimeter cube. Find the radius of the cans that will minimize the cost of the metal. Okay, we have to find what must be the radius in here that will minimize what? Minimize the surface area. We have to find what must be the radius of this one that will have a minimum metal, yeah?
Yes, metal.
Minimum metal. That means surface area must be minimum, okay?
Yes.
Okay guys, now here then let's follow the rules of what optimization. The first rule was to determine which quantity I want to maximize or minimize. We want to minimize here, yeah?
Yes.
Minimize what? The metal production. Okay, in this case I want to minimize the surface area of this one. Okay, surface area. I want to minimize the surface area. The second rule was to divide this area, surface area, in terms of some other variables. Yeah?
Yes.
Some other variables. And surface area, you know that from the geometry, it's the area of the two bases plus area of the lateral face will give us the surface area. Yes?
Yes.
Okay, now two bases we have 2 times. The area of the base is circle. That is pi r squared, yeah?
Yes.
Cylinder plus the area of the surface, a lateral surface, is 2 pi r circumference of the base times height. Height, yeah?
Yes.
Okay, now this is an area which depends on some quantities, A, R, H, yeah? And P is in here constant. Okay, 2 variables. Our A, surface area, depends on 2 variables. Now, with the given information, the next rule was, with the given information, write the A as a function which depends only on 1 variable. It's what? What is that? What is that? Radius. R, yeah? This is a function. We will find what must be the radius that the surface area will be minimum. Okay?
Yes.
Okay, now we will use the given information in our task. What is the given information?
Volume is
500 centimeter cube. That is 0.5 liters, yeah?
Yes.
Liters. Okay, so 500 to find the volume of the can. You know that it's the area of the base pi r squared. The pi r squared times height will give us the area of the volume of the can, yeah?
Yes.
It's equal to 5 centimeters squared, cube.
Yes, cube.
Okay, now I want to change here the next this variable h with r, yeah? That so that this will be the function that depends on only 1 variable. Okay, we will use this information. H is equal to 500 over
PR square.
PR squared. Okay. PR squared, that's great. Then 2 pi r squared plus
2 PR
2 PR times 500
over PR
square.
square.
Okay, that's correct. Okay, now
PR square.
let's write this. A what r A of r is equal to 2 pi r squared plus, we will cancel this one, yeah?
Yes.
Pi with this one and r with this 1r.
And
Then we will have plus 1000, yeah?
1000
R what?
R.
Okay, that's r, that's correct. Okay, now we have the function. To minimize this function, we have to take the derivative of the function, okay?
Yes.
And this will be 4 pi r plus
1000.
no, not minus r squared 1000. Is this clear?
Yes.
Okay. Now after that, I want to if I want to minimize, I have to equalize that to 0.
Yes.
Okay. 4 pi r is equal to 1000 over r squared. Now r cubed is equal to 1000 over 4p. Is this clear?
Yes.
I can cancel this one. Then we'll have r cubed. R cubed, no, 2 150 over P, and R is equal to cubic root, cubic root 250 over P. If it's clear, we are going to today study the main task, main problem. It's about this figure, prism, yeah? Yes. Okay, guys. Now let me show you something interesting. The video. The video here.
Some 2.5 centuries ago, a French astronomer, Maraldi, became fascinated with bees. One thing he noted about the double rank of cells in honeycomb is that their bottoms are not flat, but convex, formed of 3 rhombi. Obviously, the obtuse angles where bottom meets wall make it easier for the bees to construct the cells and to keep them clean. But Maraldi noted that there was a remarkable constancy to the angles of the rhombi. They measured about 70 degrees. He suggested that the bees had used this angle for the sake of simplicity. For if the acute angles of the rhombi are 70 degrees 32 minutes, the angles of the side trapezoids are identical. Réaumur, a noted French scientist, suspected that there was a further reason for the special shape. He wrote to a number of mathematicians asking what angle would give the most economical trihedral base on a hexagonal prism. Only one, Koenig, came up with an answer. To get his answer, he first proved that the volume of all hexagonal prisms with trihedral bases is the same, provided that the height h and the side A remain constant. This is easy to see. If a piece is cut off one place and put back on at another, the volume does not change. But as this distance changes, the shape of the prism and the area of its surface change.
Did you know this one? What is this one?
Honeycomb?
This one, yes. It was honeycomb, yeah?
Yes.
Honeycomb. Honeycomb means a honeycomb cell. Okay, honeycomb cell structure. You know, it's the basis. Which polygon? Hexagon.
Yes.
Okay, hexagon. Hexagon. Now we know that hexagon is the shape which minimizes the material that are needed to construct this honeycomb cell. Okay. But also one thing that is very interesting we have is its base. Base not just flat in here, not flat like in here, yeah? But 3 rhomboidal base. Why 3 rhomboidal base? We will explain that today. And also not any rhomb, but it's the rhomb. The angle, acute angle of the rhomb in here must be 70.5 degrees. Also, this one must be 70.5 degrees. Yeah? Now, I want to minimize. Now, let's find the area of this prism. Okay? Okay, Asad, you will help me in this. Okay, take this one. And yeah, Asad, now we are going to find the area of this prism. Okay? Three rhomboidal prism. Okay, come here, and you will write. First one, now, this is not just standard prism. This we have to first. We will not calculate this part. We will not use this part, this piece. We will find just area of this lateral surface and the area of these 3 rhombuses. Yeah. Okay. Now the first lateral face area. Okay. Write down. Here we have what rectangles. Yeah.
Yes.
First, how many rectangles we have?
6.
Okay, let's denote this base as A, and let's denote this as H. Then the area of this one is A times H.
Yes.
How many times we have? 6 times.
6
Yeah?
times.
6 times A times H. No, not capital letter, but smaller. let it be smaller. Okay, now 6 times 8 times h, and we have to subtract from that one this triangle. Yes, we don't have that in here. As you see, we will denote this as x because let us denote this as x, and this one is a. X times a over 2 is the area of this triangle. How many triangles we have?
3.
No, not 3. 6. Minus 6 times a times x times over 2. Okay, then what? Plus the area of 3 rhombuses, yeah?
Yes.
Area of the 3 rhombuses. What is the area? How do we find the area of the one rhombus?
Multiply the diagonals and over 2.
Oh, that's great. Okay, now that plus 3 times EF over 2. Okay, but we have to find E and F. Yeah.
Yes.
First E. Let's find this diagonal. Okay. Now let's look at here. That is the diagonal of this hexagon.
Yes.
This one. You know that this is a 120 degrees. Yes. If we divide it with this height,
This will be 60 and 60.
60 and 60, 60, 13 here, 90 degree triangle here, yes? And then, now if this one is A, over side is equal to?
A over 2.
A over 2, okay. What about this one?
A root 3 over 2.
Okay.
We have 2
yes.
base, and they will be A root 3.
Okay, that's correct. The length of this one diagonal is A root 3, yeah? A root 3. A root 3
Multiply F.
F. Okay, that's correct. Okay, let's find the F now. This is the F, yeah?
Yes.
Now we have to, if we find this one and multiply that by 2, we have the diagonal, yeah?
Yes.
This one is it's the height of this triangle. Height of this triangle.
Yes. We may cut this.
Yes. When we cut this, we will see that this is the height of this triangle, yeah?
Yes.
Whose legs are x and this one. Okay. X over 8 and x is equal to 1 over 2 over 2 over 4. 4. Okay, thanks down please. X must be equal to root 2 over 4. It's equal to approximately 0.35. Okay, then this is our function. Yeah.
Yes.
The area, surface area of the honeycomb cell. That will be the minimum when x is equal to 0.35 degree.
Yes.
As you see here on the graph, this is the graph of our function. Its minimum point of this graph is 0.35. Okay. Okay, guys. Now look at here. This is the honeycomb cell structure in carbon 3D. The area, surface area is minimum when the angle is equal to 70.5 approximately degree in this one. This surface area is minimum. Okay? As you see, the volume doesn't change, but when this angle is equal to 70.75 degrees, it will be minimum area. Okay, now guys, in here we have learned about all of this one was about functional optimization. But one more optimization problem we have that is very important. That is combinatorial optimization. In the combinatorial optimization, we have such problems very important. Traveling sales now problem. Traveling sales now problem. It's about the minimum roads between cities. Yeah.
Yes.
Between cities. Now let's watch a video here.
Begs an important question. How do they organise all this? How do they know what to do? To help answer that question, Adam's going to put them to the test.
I've set the ants a problem. I've given them a Y-shaped trail, and at one end of that Y is food, and at the other end is nothing. And I've connected that trail up to the main trail, so they're pouring down out of the nest, coming down onto this trail, and they're being faced with a choice. Do they go left, or do they go right? Our ants have a clear 50-50 choice between right and left. But after just 20 minutes, virtually all of them are heading down the path that leads to the food. The ants moving down here are laying behind them a chemical pheromone trail that marks the way for other ants. they can detect tiny amounts of these pheromones using their antennae. When an ant goes out foraging, she leaves a pheromone trail on the ground behind her that her sisters are able to follow. If she finds food, she will then lay down even more pheromone on her way back to the nest, making the original trail even stronger. If she doesn't find food, she won't lay any more pheromone, and the trail simply evaporates away. Finding the best routes to get the right truckloads to the right customers every day is a massive logistical challenge. And this challenge has a name: the travelling salesman problem. The task is to find the shortest route between a number of cities, visiting each only once, before returning to the starting point. With 5 cities, there are only 12 possible delivery routes. But as more destinations are added, the number of potential routes skyrockets. A trip with just 15 cities has over 40 billion possible routes. Air Liquide faces a travelling salesman problem that has trillions of possible solutions. So for help, they turn to the ants. Inside this computer, there is a program based on ant behaviour. It's called an ACO, or Ant Colony Optimization. The program sends out digital versions of ants to investigate potential routes. Just like our own leaf cutters, the digital ants lay virtual pheromones as they go. Shorter routes become reinforced with pheromone as more and more ants begin to follow them, while the longer routes begin to evaporate and are ignored. It's the same technique our ants use to establish the quickest route to a food source. The digital ants quickly and efficiently identify the better options. So there's no need to calculate every possible route.
We will use the ant behavior of ants to what? Minimize the road between cities. Okay guys, we are ending our lesson. Your homework is from the book from 1 to 10. And one more homework we have. That is, okay, we get here. Cylinder. This is your project homework, yeah? As you see in this sphere we have a cylinder. The volume of the cylinder in here is 0, and it's in here also 0. Somewhere in here it's maximum. You have to find what must be the ratio of the radius of the sphere to the height of the cylinder. That will maximize the volume of cylinder. Is this clear? Yes. This is your project work. You will solve that. Also we have prism in cone. And now here, as you see, also what must be the ratio of the height to the ratio of the cone that will maximize the area of this prism. Okay? Yes. And also pyramid sphere, the third one. This is your third project work. What must be the height of the pyramid to and the ratio of the height to the radius of the sphere that will maximize the volume of the pyramid. Okay? Yes. Okay.